AI Variational Autoencoders Deep Dive: How Senior Engineers Master Latent Space Learning in Modern AI Systems. Welcome back to Agentic AI World. I'm your host, and this is episode 79 of your daily AI interview prep series. Today, we're diving deep into Variational Autoencoders, VAEs, one of the most elegant and powerful generative models in the AI engineer's toolkit. If you're interviewing at companies building image synthesis, drug discovery pipelines, anomaly detection systems, or any generative AI product, this topic will come up. Let's master it. Section 1. What is a variational autoencoder? A variational autoencoder is a type of generative model that learns to encode data into a structured probability distribution and then decode samples from that distribution back into realistic data. The keyword here is probabilistic. Traditional autoencoders map an input to a fixed point in latent space. VAEs map an input to a distribution, specifically a Gaussian, defined by a mean and a variance. During training, you sample a point from that distribution and try to reconstruct the original input. This small change, from deterministic encoding to probabilistic encoding, is what makes VAEs generative. Because you're encoding distributions, not points, you can later sample from the latent space and generate brand new data. Interview insight. When an interviewer asks, what makes a VAE different from a regular autoencoder? The answer is the reparameterization trick and the KL divergence regularizer. Those two things are the heart of VAEs. Section 2. Architecture and the two loss terms. A VAE has two components, an encoder and a decoder, just like a standard autoencoder. The encoder takes in raw data, say, an image, and outputs two vectors, mu, the mean, and log variance, the log of the variance. These define a Gaussian distribution in latent space. The decoder takes a sampled point from that distribution and tries to reconstruct the original input. The training objective has two loss terms. First, reconstruction loss. This measures how well the decoder reconstructs the input. For images, you typically use binary cross-entropy or mean squared error. Second, KL divergence loss. This measures how far the learned distribution is from a standard normal distribution, zero mean, unit variance. By keeping distributions close to this prior, you ensure the latent space is smooth and structured. The total loss is reconstruction loss plus beta times KL divergence. That beta is actually important. It's the knob you turn to control the trade-off between sharp reconstructions and a well-structured latent space. When beta equals 1, you have a standard VAE. When beta is greater than 1, you get a Beta-VAE, which learns more disentangled representations. Interview insight. Be ready to explain why you need KL divergence. Without it, the encoder would just set the variance to 0 and collapse back to a regular autoencoder. The KL term forces the model to maintain spread in the distribution, which is what enables generation. Section 3. The reparameterization trick. Here's a problem. To train with backpropagation, you need gradients to flow through every operation in your network. But sampling is a stochastic operation. You can't differentiate through a random sample. The reparameterization trick solves this elegantly. Instead of sampling Z directly from the distribution with mean mu and variance sigma squared, you write Z equals mu plus sigma times epsilon, where epsilon is sampled from a standard normal distribution. Now the randomness is in epsilon, which is an external input, not a parameter. The mean and sigma are still differentiable with respect to the loss. Gradients can flow backward through mu and sigma normally. This is one of those ideas that seems almost too simple once you see it, but it was a key innovation that made VAEs trainable end-to-end. Interview insight. If an interviewer asks, how do you backpropagate through a sampling operation? This is your answer. The reparameterization trick separates the stochastic part from the differentiable part. Section 4. Latent space properties and why they matter. One of the most powerful properties of a well-trained VAE is the structure of its latent space. Because VAEs are trained to keep encodings close to a standard normal distribution, the latent space becomes continuous and smooth. This means you can do meaningful interpolation. Take 2 points in latent space, interpolate between them, and decode. You'll get a smooth transformation from one output to another. This is how you get those satisfying face morph demos. 2 faces encoded as latent vectors, Interpolate linearly, decode each point, and watch one face smoothly transform into another. You can also do latent space arithmetic. In some well-trained VAEs, directions in latent space correspond to semantic attributes. The classic example, a vector for smiling. Add it to a neutral face encoding and you get a smiling face. This is fundamentally different from GANs. GANs have no built-in structure in latent space. VAEs explicitly regularize for it. Interview insight. When asked, how would you build a system that generates variations of a product image? Think V. Encode the product. Perturb the latent vector slightly. Decode. You get controlled variations, not random samples. Section 5. VAEs versus GANs. When to use which. This comparison comes up constantly in system design interviews. Here's the honest breakdown. VAEs produce blurrier outputs than GANs. The reconstruction loss encourages the model to average over possible outputs, which leads to soft, slightly blurry images. GANs, with their adversarial training, produce sharper, more photorealistic outputs. But VAEs have a stable, principled training objective. GANs are notoriously hard to train. Mode collapse, gradient instability, hyperparameter sensitivity. VAEs converge reliably. VAEs give you explicit latent space control. You can do interpolation, disentanglement, anomaly detection. GANs don't give you the same structured encoding. For anomaly detection, VAEs are often the better choice. You encode a test sample and look at the reconstruction error plus the KL divergence. If either is unusually high, the sample is anomalous. This works because the model was trained only on normal data. For photorealistic image generation, GANs or diffusion models win. For controllable generation, structured latent spaces, and anomaly detection, VAEs win. Section 6. Production applications. Let me walk you through where VAEs show up in real systems. Drug discovery. VAEs trained on molecular graphs can encode molecules into continuous latent vectors. You can then optimize in latent space to find molecules with desired properties, then decode back to a molecular structure. This is used by companies like in silico medicine and Recursion pharmaceuticals. Recommendation systems. VAEs can model user behavior as a latent distribution. The Variational Autoencoders for collaborative filtering paper from Netflix Research showed VACF outperforming matrix factorization significantly on sparse interaction data. Anomaly detection in industrial IoT. Train a VAE on normal sensor readings. At inference, high reconstruction error signals a fault. This approach is used in predictive maintenance systems. Data augmentation. Encode real training samples. Perturb in latent space. Decode. You get synthetic but realistic augmentations that can improve downstream model accuracy. Disentangled representation learning. Beta-VAEs are used in robotics and reinforcement learning to learn representations where individual latent dimensions correspond to interpretable factors like position, rotation, and color. Section 7. Interview questions and how to answer them. Let me run through the questions you're most likely to face. Question. Explain the VAE loss function and why both terms are necessary. Answer. The loss has two parts. Reconstruction loss ensures the model actually learns to represent the data accurately. KL divergence loss regularizes the latent space to stay close to a standard normal. Without reconstruction loss, the model ignores the data. Without KL loss, the latent space collapses and becomes non-generative. Both terms are necessary for a useful model. Question. How would you use a VAE for anomaly detection? Answer. Train the VAE on only normal data. At inference, encode a new sample and compute two scores, reconstruction error and KL divergence from the prior. Normal samples will have low scores because the model learned to represent them well. Anomalous samples will have high scores because they fall outside the learned distribution. Set a threshold on the combined score for flagging. Question. What is a Beta-VAE and when would you use it? Answer. A Beta-VAE multiplies the KL divergence term by a factor beta greater than 1. This increases pressure on the latent space to disentangle independent factors of variation. The trade-off is slightly worse reconstruction quality in exchange for more interpretable and controllable latent dimensions. Use it when you need disentangled representations. For example, when you want individual latent dimensions to correspond to semantic attributes like shape, color, or size. Question: what are the failure modes of VAEs in production? Answer: 3 main ones. Posterior collapse. The decoder becomes so powerful it ignores the latent code, causing the encoder to output the prior trivially. Fix with KL annealing or free bits. Blurry outputs. Reconstruction loss averages over modes. Fix with perceptual loss or a hybrid VGN. And latent space fragmentation in high dimensions. Mitigate with hierarchical VAEs or normalizing flows. Section 8. Advanced topics for principal-level interviews. If you're gunning for staff or principal engineer roles, go deeper. Hierarchical VAEs. Standard VAEs use a single latent variable. Hierarchical VAEs, like NVAE or VD-VAE, stack multiple levels of latent variables, each capturing different scales of variation. These produce significantly sharper outputs. Flow-based VAEs. Replace the Gaussian prior with a more expressive distribution using normalizing flows. This gives more flexible latent geometry and better sample quality. VQ-VAE, vector quantized VAE. Instead of a continuous Gaussian latent space, VQ-VAE discretizes the latent space into a codebook of learned embeddings. This is the architecture behind many modern image and audio generation systems, including the discrete representation used in DALL-E 1 and Audio VAE. Conditional VAEs, CVAE, condition the encoder and decoder on additional information, like class labels or text prompts. This gives you controlled generation. Generate faces of specific age groups. Generate molecules with specific properties. Section 9. Quick implementation notes. When you're implementing or reviewing VAE code, watch for these details. Use log variance, not variance directly. Variance must be positive, but log variance can be any real number, easier to predict with a neural network. Compute sigma as exp of log variance divided by 2. KL annealing. Start training with 0 KL weight and gradually increase it. This prevents posterior collapse early in training when the reconstruction loss dominates. Choose reconstruction loss carefully. Binary cross-entropy for binary inputs like binarized NIST. Mean squared error for continuous data. Perceptual loss. Features from a pre-trained network. For natural images when you care about visual quality. Monitor both loss terms separately during training. If KL diverges to 0, you have posterior collapse. If reconstruction loss plateaus high, your decoder capacity may be insufficient. Wrapping up, variational autoencoders are a fundamental generative model that every AI engineer should understand deeply. The key ideas are probabilistic encoding with mean and variance, the reparameterization trick that enables backpropagation through sampling, and the dual loss of reconstruction plus KL divergence. In production, VAEs excel at anomaly detection, controlled generation, and learning disentangled representations. That's episode 79. Tomorrow we go deeper into the architecture family, diffusion models, how they work, why they beat VAEs and GANs for image generation, and how to design diffusion-based systems in production interviews. If this helped you, subscribe so you don't miss a single episode. And if you're prepping for a system design interview this week, go back and listen to episodes 30 through 35 back-to-back. That sequence will cover the full stack of production AI system design. I'll see you tomorrow.